Okay, for this video, we'll be going through 2020 for your TYS. Make sure you have actually reviewed all the mistakes in your previous paper before you embark on the next paper. Okay, that means you look at like maybe 2018 and 19, and then you look at which chapter you always get it incorrect. Okay, be it explanation or be it formula. Then you can do a quick revision in that chapter, and before you so that when you try the next paper you do not make the same mistakes. Okay, so you have to do this for every paper, right? Okay, let's start. Okay, question says blocks of salt are used in a water softening system. The dimension of each rectangular block are 9 cm, 9 cm, and 27 cm. So it's good, everything is in cm. Okay, and the mass of each block is 4 kg. So this is my m. Calculate the density of the block of salt. So density equals to mass over volume. But before we do that, we see that it is in grams per cm cube. The answer, they want you to leave it in grams per cm cube. So I need to change my mass to 4,000 grams. And volume will then be 9 times 9 times 27. Basically, is your length times breadth times height. Okay, and that will give us a value of 1.8 grams per cm cube. So this is 2 marks, very easy. So if I see this in my first question, I must do it and I must score so that it gives me some confidence. Yeah. Now the block may be placed on a horizontal surface with any of its faces in contact with the surface, right? So calculate the largest pressure. So pressure is P, so please make sure you annotate. They want us to find the largest pressure. So what is the formula for pressure? Equals to force over area. And this is where a lot of students will make mistake. They'll just take the mass and substitute in as a force. Okay, so weight is actually a force, which is W. So it is my mg over A. Therefore, my pressure will be mass, and the G is given and A. Okay, but the mass, make sure that it is in kg. So maybe I substitute in my 4 first, my 10. And now for area. Okay, so look at the units that you're supposed to give it in. You're supposed to give it in Newton per cm square. And as you know, the unit for weight is already Newton, which means mg unit is already Newton. So this 4 times 10, the unit is actually Newton. Now we need to make sure that the area, we leave it in cm square. That means we don't even need to convert it to meters, okay, or meter square. So it's easy, but they want maximum pressure, which means my area must be, if they want maximum pressure, my area must be the smallest. Okay, so which side will give me the smallest? We have 9, 9, and 27, so definitely will be 9 times 9. Okay, so the answer will be, so you can see 40 Newton over 9, which is, in the end, will give me 0.49. Okay, so sometimes it's good to look at the units first before you do your conversion. Okay, part C, when the block is in position to exert the largest pressure, okay, so it's falling from part B, it is in its most unstable position. Unstable, so this has got to do with stability, right? Then you must think, what makes something stable? Okay, there are 2 factors that make something very stable. So if I want something very stable, then the CG must be low as possible. Okay, and next thing is the base area in contact with the ground. Base area must be as large as possible. Okay, so I can actually use a very simple diagram to show you. So here I have a triangle, right? And if I were to put it in different orientation, so the CG will be somewhere here, right? Where most of the mass is. Okay, so if you see, if I were to compare, it's the same object, but A, the CG above ground is the highest, right? This is the height where the CG is. For B, the height is low. Okay, so if I have CG as low as possible, it's going to be very stable, right? Common sense tells you that B is actually more stable than A. And in addition, the base area for B is larger than the base area of A, which is this small tip. That's why this thing will always topple, right? But for B, it will just stay stationary. So they want us to explain why the block is unstable. So do you realize that if I were to put it in that orientation, it will look like this, right? So this is 9, and this is 27. So when I have it in this place, in this position, the CG is actually very high, which is actually 13.5 cm above ground, right? And the base area is 9 times 9 is 81 cm squared, very, very small, okay? But if I were to put it in the other orientation, I will have larger pressure, smaller pressure, but it will be more stable. So this is my 9, and this is 27, right? So if you were to compare, the CG will be somewhere here, which is actually 4.5 cm above ground compared to 13.5 just now. And the base area will be 9 times 27, which is 180, will be about 200 plus cm square, okay? So this will make this even stable, but you will have least pressure, right? This will be maximum pressure, but the least stable, okay? So how do we explain this? Therefore, we must have our keywords. Let's look at what the keywords will be, okay? The block is the most unstable in this position, right? The one whereby it's standing like that. Okay, why? Because the center of gravity is the highest, okay, while the base area is the smallest. Then what happens? A small tilt will cause the line of action of the force due to weight to lie beyond the base. So how does it look like? So if I have this thing here, and I'll just draw the cross, just draw the simple one like that. The CG is here, the line of action of the force, you see, it will fall outside of the base area, right? So a small tilt will cause the line of action of the force due to weight to lie beyond the base, which will then create a toppling turning effect, which will cause the block to fall over. So what's the remark? Some responses stated that the surface area was smallest, okay, without specifying that this referred to the base of the area of the base. Please do not use surface area, okay, because whatever orientation I put it in, it will have the same surface area. It is the base contact area. Some responses did not state that the center of gravity is the highest at this position. So there are actually 2 points: the base area in contact plus the center of gravity, okay? Let's go to question 2. A girl standing on a cliff top holds a pebble at a height of 30 meters above the shore. So this is my H. As shown in figure 2.1, the mass of the pebble is 200 grams. So this is actually 2200 kg. So this is my mass. Okay, why do I change it to kg? Because I suspect it is a work, energy, and power chapter question. Okay. So she drops the pebble, calculate the loss of gravitational potential energy of the pebble as it falls from her hand to the shore. So what is the energy that this pebble has initially? It will have gravitational potential energy, right? Because it is held above the shore at a height of 30 meters. So I will use my formula mgh, and this is a SI unit chapter. Okay, please take note. So the mass is actually 0.2, the G is 10, the height is 30 meters. So everything is in SI unit. So I'll get 60.0 joules. So like that will be 2 marks. So the loss is because it went from this position all the way down. So where did this GPE go to? Okay, it will actually be transferred to the kinetic store of the pebble. So they want us to ignore any effects of friction. That means we ignore air resistance as well. We calculate the speed of the falling pebble when it is at a height of 20 meters above the shore. So let me do a quick sketch. This is the pebble. Okay, so you can always draw a quick sketch to guide yourself. So now it is 20 meters. That means it has fallen by 10 meters. Okay, that means it has this amount of GPE that is being transferred to the KE. And with the KE, then I can find the speed of velocity. Okay, So how much is this GPE? How much of GPE is transferred to KE? So MGH equals to 0.2 times 10 times 10, right? Because this is the height, this is the G, this is the M. So I will get 20 joules. Okay, so 20 joules is then transferred to the kinetic energy. Okay, energy in the kinetic store. Then what's the formula for KE? KE is half mv square. That means it's going to be half. This is going to be 20 joules, right? M is 0.2, and my V will then be the only unknown. So V will be, if you do your math, it should be, let me see the answer, 14 meter per second. Okay. Two SF, 2 or 3 SF is okay. So that's why they give 3 marks. There's a lot of things to talk about here. Firstly, when it is at a height of 20 meters above the shore, that means it has fallen by 10 meters. This is what you need to know. And this is the amount of GPE that is being transferred to the KE, right? And if I know the KE, then using the formula half mv squared, then I can find the speed. So exactly how much GPE has been transferred to KE, I apply my MGH again. I will get 20 joules. So 20 joules is given to the KE. So I substitute in KE as 20 joules and equals to half mv squared. Then I'll get this answer of 14. Let's see the remarks. Any remarks? Okay, so only a minority of candidates realize that when the pebble was 20 meters above the ground, it had fallen a distance of 10 meters. So common mistake was to take the loss in height to be 20 meters. That means they didn't read the question carefully. Okay, now some students try to work out speed by using a formula speed equals to distance over time. This only works for constant speed. Okay, so this is PSLE level. Okay, let's look at question 3. Question 3 is no longer in syllabus because you don't have to draw your vector diagram. So we go to question 4. So your total mark should be 65 minus 3. So far is 62, yeah? So figure 4.8 shows how the pressure of air near a loudspeaker changes with time when a note is sounded. So this one looks quite familiar. Not sure if this has come out in previous year. So this is time. So this is pressure versus time, right? So with time, I can actually find period because this is wave, right? If I can find period, which is T, which is the time taken to complete. Remember, period is the time taken to complete one wave. Okay, so if I start from here, 0, then this will be one complete wave. Okay, so it is 1 millisecond. Therefore, the period is 1 millisecond. Take note of the milli, right? So how can you find frequency? Frequency will then be F, which is frequency, will be 1 over period. Okay, so since I have my period T to be 1 millisecond, which is 0.001 seconds, frequency is 1 over period, therefore it is 1 over 0.001, which then is equals to 1000 hertz. Okay, so if you know your dd and dt graph for wave, and you know that this is something like a dt graph, then you will be able to get your period and therefore your frequency. Okay, so this is something that you can do. Now the loudness of the same note is increased. On figure 4.1, draw a second waveform to show how the pressure changes with time. So take note, it is only loudness. Loudness is affects the amplitude of the wave. Okay, amplitude of the wave. Therefore, I must draw something that is of higher amplitude. That means here, maybe something like that. Okay, and then it must have the same frequency. Okay, so frequency should still be the same. So something like that. that means your period should still be the same. There should be no change to the frequency. Okay, so the amplitude must be increased. Therefore, the pressure is increased. So this will get you your 1 mark. Now, a different sound wave has a frequency of 3200 Hz. Annotate, this is my F, and it's traveling through water. The speed of sound in water is 1600 meter per second. So this is my V. Calculate the wavelength. If you annotate and if you memorize the formula, these 2 marks should be very simple. Okay, I've seen a lot of students for consultation and a lot of them still don't annotate. I don't know why. Okay, when you annotate, you know who they are, then you can apply them into the formula. Okay, so my will be 0.50. Okay, my math is correct. Okay, so just now for the drawing, a small number drew periods that were not the same, particularly at the end. Okay, so what is the instruction? They want draw a second waveform to show. Therefore, I shouldn't just stop here. I need to continue. Okay, my amplitude should be the same. Okay, but more importantly, my period should be the same. So something like that. Okay, so something like that, yeah. Okay, so after that you do your V equals F lambda. So you see a small number divided the frequency by the wave speed, and even fewer multiplied the quantities together. So a very small number, leave the answer as a fraction or left the answer in 1 SF. That's what I mean. Okay, leave your answer in 2 or 3 SF. Now that your practical is over, you don't need to care about the precision, you don't need to care about the SF, you don't need to care about the DP. For theory paper, everything either in 2 or 3 SF, never fraction. Okay, please. Okay, let's go to question 5. Solid substance is heated until it becomes a liquid. The variation with time of the temperature of the substance is shown. Okay, so this is actually your heating curve. So one thing that you need to take note here is, if you have missed out, then this is very significant. It is a solid. So it is solid here, then here is solid plus liquid, and then here is liquid. What happens if somebody didn't read this and they thought it is liquid? Then you'll be liquid plus gas and then gas. So this is incorrect. Okay, so whenever you have this kind of 2 stages one, then you need to make sure you read to know what is it in the initial state. Okay, then I want to talk about this heating graph. When it's a slope, it's only one state. That means there's change in temperature, no change in state. Okay, so please write this down if you didn't get it correct. When it is flat, it is 2 states. It is changing state, no change in temperature. Okay, by now, if you have done enough paper, you have noticed that whenever they ask this, it's always the same kind of question. So if you still do not know this, please write this down. Now, describe how the motion of the molecules of the substance changes during the first 2 minutes. So first 2 minutes, we are talking about the solid state. Okay, so pay attention to this, first 2 minutes. So it is, we are talking about solid, no change in state. Okay, means the particles are vibrating more vigorously, right? And since they want to describe, we need a lot more details. They are vibrating more vigorously. Come, let's take a look at the answer. Okay, so this is important. They vibrate faster. Why is it faster? Because as temperature increase, kinetic energy increase. Okay, kinetic energy of the particles increase. Why do I not use energy in the kinetic store? Because when now we are talking about particles, we can directly say their kinetic energy, we can directly talk about their potential energy. So when do I use store? I use store when I'm talking about the object, because the object contains many small particles. The object is a store of many particles, right? Therefore, I need to talk about their kinetic energy in the kinetic store, energy in the potential store. But for particles, they are just by themselves. So the particles possesses energy. Okay, so they have kinetic energy, they have potential energy. So when I'm talking about particles, I drop the store. Okay, come back to this. The particles vibrate. When can I use vibrate? It's only for solid. Okay, they vibrate faster about their fixed position as the temperature rises. So look at the remark. Stronger responses stated that the molecules will vibrate faster. Mistakes. Many others simply stated that the molecules vibrate about their fixed position. So without giving description, which means it is faster because temperature increase, kinetic energy increase. So they actually did not address the question. So they lost 1 mark without writing faster. The most common mistake was to state that the change of state was happening. Right? So if it's slope, there's only one state, no change of state. Was happening in the first 2 minutes, and to describe the change in molecular arrangement. But they didn't ask about this, right? The question say how the motion. So they either ask about motion or arrangement or both. Okay, so you have to distinguish what is motion, what is arrangement. Now, the temperature of the substance remains constant between time 2 minutes and time 6 minutes, right? So, like what I say, when it's flat, there's no change in temperature from 2 to 6 minutes. So, explain why the temperature remains constant. If this comes out for O level, you must score. This is a very, very typical question because the substance is undergoing melting. Okay, you can recognize that it's going from solid to liquid, so you will know the process is melting. So write this down, be explicit as possible. And then what happens during melting? All the thermal energy supply is used to break the intermolecular bonds between the particles, causes the particles to move further apart and change state from solid to liquid without a change in temperature. Okay, the internal kinetic energy of the substance remains constant. Right, because temperature affects kinetic energy. The state affects potential energy. And just to do a very quick recap, solid, liquid, gas. If you still do not know this, please write this down. Solid, liquid, gas. Gas has the maximum kinetic energy. It also has the maximum potential energy. Right, the particles are the furthest apart. Okay, so it will actually have the maximum potential energy because the particles are furthest apart. Okay, so if you do not know this, please write this down. Okay, stronger answers show a clear understanding that energy is needed to break the intermolecular bonds. So you can use break intermolecular bonds. I think for chemistry, you'll actually use overcome, right, intermolecular bonds. Mistake, some answers fell short of complete understanding by incorrectly stating that kinetic energy is gained. There is no change in temperature, so how can kinetic energy be gained, right? A small number simply describe the arrangement without answering the question. Okay, so please read the question. You must score for this kind of question. Now, explain using kinetic theory why a liquid can flow but a solid has a fixed shape. Let's look at the answer. Okay, so liquid particles have weaker forces of attraction. So you see, for the kinetic theory, right, they like to ask you about Ke, which is linked to temperature. They like to ask you about Pe, which is linked to change in state. Correct? Then they like to ask you on forces of attraction. Right? They like to ask you on the motion. They like to ask you on the arrangement, right? So all these are the concepts that will be tested. So if you know all this, basically you can score in this chapter. So liquid particles have weaker forces of attraction between the particles compared to solid particles, right? So these weaker forces of attraction allow the particles in liquid to slide past one another. You cannot use vibrate for liquid particles, yeah? Therefore, the liquids can flow. In solid, the stronger forces of attraction hold the particles together in fixed position. Hence, solid has a fixed shape. So basically, everything you know about this chapter, you can write down here. Now, weaker answers simply give everything the candidate knew about the arrangement of molecules in solid and liquids. Sometimes the answer include the correct signs, sometimes not. Stronger candidates, take note, make sure that they use their knowledge of physics to answer. Don't know what's that, which is basically forces of attraction. Okay. Okay, then we can go to question 6. Okay, complete figure 6.1 to show the light incident on face BC and emerging into the air. Okay, so maybe it's time to do some recap on this chapter, right? So because previously I think not many questions will talk about light. So light, I will talk about it in, there are 3 parts. Firstly is reflection. Okay, what is reflection? Reflection, when do you know it's reflection? When you see things like a surface, okay, you see things like mirror, okay, so then you will know it's reflection. What will they test you on reflection? They'll test you on the 5 characteristics of plane mirror image, okay, which is, I like to list in this order because it's the shortest to the longest. Upright, virtual. Okay, upright means the same orientation. Virtual means cannot be captured on a screen. Please memorize this. Some students will say, oh, virtual means not real. But that's not the definition. Real means can be captured on a screen. Virtual means cannot be captured on a screen. Third is same size. Fourth is laterally inverted. That means your left is the right, your right is the left, laterally inverted. Lastly is equal distance, right, of image to mirror and object to mirror. Okay, so they will test you on the 5 characteristics. Then they will also test you on the laws of reflection, which is, you can find out. Got 2, okay, which is basically what is important is angle of incidence equals to angle of reflection. The other one, you just need to memorize it. Okay, so then what will they test you? What else can they test you? They can test you on how do we find where is the image, okay, or how the light rays enter the eye. So example, I have an object here. This is object, yeah. Then I have an eye over here. So if you use a mirror, okay, what do you use the mirror for? It is to see where to look at the image, right? You don't want to look at the object, right? Basically, you use the mirror to look at the image. So if the object is there, so you have to apply number 5 lah. And one thing that's important is draw your normal. Normal is a perpendicular line which is imaginary, okay, and it's 90 degrees to the surface. So this is my normal. Okay, I draw it with a dotted line because it's imaginary. I draw equal distance. You see that it's roughly equal distance. So like what I say, how do what do you use the mirror for? You use it to look at the image. So you will draw a line, okay, and this light ray actually enters the eye. So why do I have dotted here? Because the image is virtual. There's not really something real there, okay, and this therefore must also be dotted. Okay, so where did this light ray actually come from? It came from the object. So it is it bounces off the mirror. So I will get my angle of incidence, and this is my angle of reflection, and this is my normal. So this angle of incidence must always be between the incident ray and the normal. Okay, so example, I think later on, I think there may be one question, okay, or like this. So I have an incident ray, okay. What is the angle of incidence? So some students will just, oh wow, this is nice, you give me the angle, so angle of incidence is 20 degrees. Now this is not correct, right? Because the angle must always be taken from with respect to the normal. Okay, so this will then be 70 degrees because normal is 90 degrees. So please think of that. You draw the normal, or the normal is there to serve a purpose. It's used as a reference line for you to see where is the angle of incidence and where the angle of reflection is. Okay, so basically this is what they'll ask for, reflection. Then what will they ask for? The next part. They will test you on refraction. Refraction is the bending of light ray as it enters an optical medium from another optical medium. Okay, from one medium to another lah. Why I use optical? Because we are dealing with light. Okay, later I'll explain more. So refraction is the bending of light as it enters an optical medium from another optical medium. What is the why? Why does it bend? Why bend? So this is what is refraction. Okay, it's the bending of light ray. Why does it bend? Because as it goes from one optical medium to another, the speed of light changes. Okay, so what are some examples of optical medium? We have examples like air, we have vacuum. So air and vacuum, they are actually a medium whereby for vacuum there is no particles, right? For air, there's also very little particles. So the speed of light, or light can passes through these two medium very quickly because there's not much particle to block their path, right? So the speed of light for vacuum is 3 times 10 to the power of 8 meter per second. Okay, and we like to use the value of c, not value, we like to call it c. Okay, so speed of light in vacuum is c, is 3 times 10 to the power 8 meter per second. It is useful to memorize this value, 3 times 10 to the power 8 meter per second. Yeah, so we have this formula, n equals to c over v. Okay, so n is the refractive index of the medium. Okay, so what is the refractive index for vacuum? And vacuum, the value is 1. And air, which is the refractive index of air, is approximately 1 as well. Okay, not much difference. It's higher than vacuum, 1 point something, 0 something, blah blah blah. Okay, but we can take it as 1 because everybody stays in air. Okay, nobody stays in vacuum. Okay, that means this n will be the refractive index of other medium, example water, glass, plastic, or diamond. Okay, and the thing to take note here is that the c must be the speed of light in vacuum. So we use 3 times 10 to the power of 8. And if then this v will be the speed of light in that medium. Okay, so please take note, the speed of light in vacuum is the fastest. There's nothing faster than that really. That's really the fastest, 3 times 10 to the power 8. Therefore, if it passes through glass, water, plastic, or diamond, the speed will slow down. So that means this one will be less than 3 times 10 to the power 8. Less than 3 times 10 to the power 8 meter per second. So this is 3 times 10 to the power 8. This is less than that. Therefore, refractive index of water, glass, plastic, and diamond will definitely be more than 1. So if in your calculation you encounter when you calculate your refractive index, you get less than 1, you know your formula you apply incorrectly. Okay, so this is the first formula they like to ask you. So later we see how we can apply that. The other formula is your n1 sine theta 1 equals to n2 sine theta 2. Okay, so when you see sine, it is your math, your trigo. So this is your angle, this is your angle. Okay, so what is N1 and N2? So N1 is the refractive index of medium 1, N2 is the refractive index of medium 2. Theta 1 is the angle in medium 1, theta 2 is the angle in medium 2. Okay, I know some students, their tutor may teach them n equals to sine I over sine r. I used to teach that as well, but later I decided not to use this. I straight away use this because it is more straightforward. Okay, and does it matter whether who is medium 1 and who is medium 2? It doesn't matter. Okay, so let's see how we can apply this to So basically they will ask you on reflection and refraction, and also refraction, there's a laws of refraction. There are two laws. Okay, and the one that's important to us is basically n equals to sine I over sine r lah. You can read about it. Okay, so usually they won't really ask you to quote laws of refraction. They will ask you to apply it, but laws of reflection they may ask you to quote it. Okay, so let's take a look. Oh, there's also this thing called LDDT, which I think only my students know. Which means less dense to denser, the light will bend towards where? Normal. So whenever you see refraction, how do you know it's a refraction question? Basically, the light is going from one medium to another. There may not be mirror. If it's mirror, then most likely it's reflection. But if it's going from one medium to another, then you know that it must be refraction. Okay, so this is a glass prism. So glass, as you know, it must be denser compared to outside, which is less dense. So if it's going from less dense to denser, it will bend towards the normal. So they have very kindly draw the first normal for us at the surface AB. But take note, every surface, every time the light passes through a surface, you draw a new normal. Okay, you draw a new normal. So just to recap, this is my angle of incidence and this is my angle of refraction. Okay, angle of incidence, angle of refraction. It is always taken with respect to the normal. Very important. Okay, so let me draw the original path. So by right, as it goes, light travels in straight line, right? But because it's going from a less dense medium to a denser medium, LDDT, it bent towards the normal. That's why it bent towards the normal. So this is the original path. It would have traveled like that if there is no glass prism in its path. But now that there's a glass prism, it's entering from air into glass. So it's entering from a less dense medium air to a denser medium glass. And according to my LDDT, it should bend towards the normal. So you must draw your original path and then draw it bending towards the normal. Okay, so let's continue. Let's say now the light ray travels straight. Yes, and this is where it is crossing a boundary. So every time it crosses a boundary, you must draw a new normal. Okay, a new normal. So tell me, when it passes into crosses boundary BC, it's now going from denser to less dense. Now, if it's going from less dense to denser, it bends towards. So if it's going from denser to less dense, it must bend away. It must bend away. But I only ask you to memorize this because I don't want you to go and memorize DLDA. Denser to less dense, it bends away. Then you will be confused. So just memorize one. And if it's going from denser to less dense, then you denser to less dense, then you just reverse. Okay, I hope you understand what I'm saying. So I've drawn the normal. I will also draw the original path as if there is no difference in medium. This is the original path. Okay, so it's going from denser to less dense. That means it must bend away. So it will have to be like that, right? Because this is original, it must bend away from the normal. Normal is here. So it's very important. You must draw your normal. You must memorize your LDDT, and you must then apply it. Okay, so like that is just 1 mark. But if you know the technique, it's very fast, it's very easy. Okay, let's look at part B. The light travels from water into glass. Water into glass. So this one is quite tough. This one is quite tough. Okay, this question was tough because I always tell my class that one of the medium will always be air or vacuum. But now, both of them are actually mediums that are not air or vacuum. Alright, so then this is water, is actually dense, less dense compared to glass, denser. So remember just now I told you about this formula, N equals to sine I over sine R. Okay, so this formula is when the light is going from less dense into denser. Okay, so this N is for the light traveling from water into glass. So this is N. So this question you might want to take note of it. So even though I teach N1 sine theta 1 equals to N2 sine theta 2, where one of the medium will either be air or vacuum. Okay, but sometimes O level they like to trick us lah. So they use water and glass in this case. And I know water is less dense, glass is denser. Okay, because if for me, I'm able to move in water much more freely, but I'm not able to move in glass as freely. Okay, so that will give you some idea of their optical density. So they want us to calculate, so I will have to use this formula, N equals to sine I over sine R, and then the answer will be 62 sine 62 over sine 47 to get 1.2. Okay, so this one I just need you all to take note that a few students sometimes accidentally set the calculator to radian mode. Okay, so always have to be in degree mode. Okay. Okay, let's look at question 7. The battery in the computer is recharged using a 5-volt charger. So this is my V. Please annotate in 25 minutes. So this is my time, and I know I need to change it to seconds. Okay, 1 minute is 60 seconds, so 25 times 60, so it's number of seconds. The charger transfers 3300 coulomb of charge, so this is actually my Q. So I have V, I have Q, I have T. So calculate the average charging current, which is I. So the formula is Q equals to IT. Okay, I cannot overemphasize the importance of annotating the values. Okay, you must know their identity. So this is 3300. The I is unknown. The T is 25 times 60. This is a SI unit formula. Okay, you need to know this so that you can convert whatever values you have into SI unit. So the current will then be 2.2 ampere. Okay, so like that you get 2 marks. The energy that is transferred to the battery, what are the formulas that we learn? We have one which is the V equals to work done over Q, right? So energy is actually work done, so this is what I'm supposed to find. I have the Q, which is 3300. I have the V. So what is the energy? It will then be V times Q. Okay, so you should get 16500 joules. So if you know the formula, you can score for these 4 marks, yeah. But take note, must be in SI unit. Okay, question 8. Hot gases containing smoke particles pass out a chimney as shown. So this metal plate is high positive charge. This is high negative charge. Okay. Then we have the motion of the charged smoke particles. Some are positive, some are negative. Okay, so this is positive, blue, red, I call it negative lah. So all these are the negative. Okay, then all these are the positive. And it is important to take note that like charges repel. Unlike attract. Unlike charges, attract. So I have two metal plates attached to the side of the chimney. They are connected to a high voltage supply. Smoke particles are electrically charged. Some carry positive, some carry negative. Explain how this arrangement removes smoke particles from the hot gases as they pass up the chimney. 2 marks. That means I must have 2 points. So definitely one of it will be unlike attract. Okay. So let's look at the answer. Since unlike charges attract, you need to state this. The metal plates connected to the high positive voltage will attract the negatively charged smoke particles, while the metal plate connected to the high negative voltage will attract the positively charged. Now, this is still one concept, so that's why only 1 mark. Okay, then the smoke particles will remain attracted on the plates and so are removed from the hot gases. Okay, so look at the comments. Almost all knew that positive charges are attracted to the negative plate and that the negative charges are attracted to the positive plate. I think this one a lot of people know. A small number showed some confusion by writing about like or unlike poles. We are not talking about magnets. Okay, so like that will get your marks deducted. Very few candidates went on to answer the question, which was to explain how the arrangement removes smoke particles from the air. That is how you get your 2nd mark. Only a small number point out that the smoke particles remain on the plates and so are removed from the air. So this is actually important, right? A number of candidates tried to explain this by repeating the stem of the question without answering the question. What is the stem of the question? Explain how this arrangement remove smoke particles. So if you just say, oh, this removes smoke particles, no, you must say that they remain attracted to the metal plates. Okay, they remain attracted on the plates. Okay. Okay, so now I think this is DC. So I have 9 volts here. Resistor X is resistance 500 ohm. With component Y, what is it? I don't know. And a 9 volt battery. Okay, the resistance of component Y will vary with temperature. Okay, so we see that as temperature increases, right, resistance for Y decreases. Okay, so determine the temperature at which the potential difference across X is equal to the potential difference across Y. So this is our sum. In how are they connected? They are connected in series. In series, current is same. Voltage is sum. So therefore, Vx plus Vy will be equal to 9 volts. Okay, that means if I want the potential difference across X to be equal to the potential difference across Y, so then Vx should be 4.5 volts. Vy should be 4.5 volts, right? Because they add up to be equal to the 9 volts because voltage is sum. So if Vy is 4.5 volts, okay, that means the current, so Vx is 4.5 volts, okay, and Rx it's 500 ohm. That means Ix, the current that flows through resistor X, will be Vx over Rx because of the formula V equals IR, right? So 4.5 over 500, I will get a value of actually I don't need to do so much, because if they are the same resistance, then they will share equally the 4.5 volts, equally the 9 volts. Okay, that means it must also be at 500 ohm. I'm overthinking things here. Okay, so actually the temperature, if you read it correctly, it will be about 14 degrees. Okay, 14 degrees. A small number misread this temperature as 12 degrees or 10.4 because they never look at the scale. Okay, so like that loses 1 mark. Okay, next, for a temperature of 60 degrees, determine the resistance of Y. So let's look at 60 degrees. If it's at 60 degrees, so read it carefully, it is at a resistance of 100. Okay, so it is 100 ohm. Yes. Okay, so that's B part 1. Now B part 2, calculate the current in Y. So I will recommend you to redraw. So this is my X, Rx, it is 500 ohm. And this is my Y, it is now 100 ohm at a temperature of 60 degrees. So this is actually equivalent to 600 ohms, correct? Why do I do that? Then it is very simple. I can apply my V equals to IR. I have my V, I have my R, which is 600 ohm. Because they are connected in series, so I can just add them up. But for parallel, you need to do your 1 over R1 plus 1 over R2, then you flip. Okay, I hope you know what I'm talking about. So I can calculate the current to be 9 over 600. Okay, so the value of the current will be 0.015 ampere. And because they are in series, so the current that flows through X must be equal to the current flowing through Y. Okay, so some students, they will actually divide 900 by 9 volt by 100. Okay, because they don't understand that this 9 volt is actually to be sort of distributed to 500 and 100 ohm. So the most straightforward way is to add up the resistor, get it into one single resistor. Okay, so the current will be 9 over 600, which is 0.015. Okay, calculate the potential difference across Y. Still the same thing. So if the current that flows through flows through Y is 0.015, then Vy will be Iy multiplied by resistor Y. Vy is unknown, 0.15, 0.015 multiplied by 100, so will be 1.5 volts. Okay, 1.5 volts. Now, how about the Vx there? Let's just do Vx. Vx will be Ix multiplied by Rx. Okay, Ix multiplied by Rx. So Ix is actually 0.015. It is equals to Iy. In a series, current is the same. Rx is 500. So I will get 7.5 volts. If you add up 1.5 volts and 7.5 volts, you get equivalent of 9 volts. Because in series, voltage is the sum. Okay, so this one will be 1.5. Okay, so if you understand all this, well, straight away 5 marks, you know. Now, this one I explain how the potential difference across resistor X changes as the temperature of Y increases. Just now we saw that as temperature increases, the resistance of Y decreases. Okay, that means the potential difference across X will, Vx will increase, right? Because if my resistance get lesser and lesser, then I will have a larger current flowing through, right? Because the total current, it is affected by the total resistor. But my V is the same, V equals IR. So this R, if it decreases, my V is the same. My current that flows through will increase. That means now, if I have a fixed resistance of 500 multiplied by the current, I will get a larger V. Okay, let's see how to answer. As the temperature across Y increases, resistance of Y decreases. The effective resistance in a circuit will decrease, right? The effective resistance is Rx plus Ry. And hence the current through the components will increase because they are connected in series. Therefore, the current is the same in both components. And because the effective resistance decreases, therefore the current will increase because V equals IR. So this will cause the potential difference across resistor X to increase since V equals to IR. As the current through X increases, potential difference across X also increases. Now, I told you many times that for a lot of explanation questions, it is good to bring in the formulas. And actually, you see that the formulas are all over here. V equals IR, V equals IR. Okay? Now, stronger responses realize how the PD across X changes with temperature of Y. Weaker responses use it without making clear which resistor it refers to. Okay, so it must be very explicit. Some stated that the current remained the same, which is not true. A small number erroneously stated that the resistance of X changes, which is not true. It's a fixed resistor. Minority believe that if the PD across Y decreases, the PD also across X must also decrease. No, because it's a sum, right? Okay, let's look at question 10. Okay, so electromagnet AB consists of a coil of wire wound on a soft iron core. So need to take note soft iron core. Soft iron means easy to magnetize, easy to demagnetize. Okay, the coil is connected in series with a switch and a direct current as shown in figure 10.1. One end B of the electromagnet is close to the north pole of a bar magnet. So now we use pole, not charges. When a direct current passes through the coil, NB becomes a magnetic north pole. The current in the electromagnet is switched on, state the effect on the bar magnet. Okay, so this is positive, so current comes out this way. If the switch is closed, current will flow. I need you to draw all this direction of the arrows on the coil here, right? Because we need to apply right hand grip rule. So right hand grip rule, your fingers, I'm using my right hand. Okay, so this is my right hand. The thumb represents north. The fingers represent direction of current. I must add, this is the right hand grip rule for solenoid. Okay, we also have right hand grip rule for straight wire. Okay, how does it work? If I have a straight wire, obviously it doesn't look like a solenoid, it's just a straight wire with the current flowing through. Okay, so in this case, my thumb represents the direction of current. So this is my fingers now. I'm gripping it. I'm using right hand. Okay, my fingernails. And this is my thumb. Okay, so my thumb now represents direction of current. This is right hand grip rule for straight wire. Right hand grip rule for solenoid, my thumb represents the direction of north, where north pole will be. So this part will be south. Okay, but over here my thumb represents the direction of the current, and this one will then represent, my fingers will then represent direction of magnetic field. Why is there a magnetic field? Okay, so I always ask this in class. Whenever current flows, it will produce a magnetic field. So the current can either be flowing in a straight wire or it can be flowing in a solenoid. So whatever the case is, it will produce a magnetic field. Then how do I know how to draw the magnetic field, or where's the north, where's the south? You will then have to see whether is it solenoid or is it straight wire. For straight wire, you must apply it like that. For solenoid, the thumb represents north, blah blah blah. So now if I were to apply this, I will indeed get B to be a north pole. So this is 2020 paper, right? They are very kind to us. They tell us that B is north. So the current in the electromagnet switch on, state the effect on the bar magnet. So the bar magnet will be repelled because like poles repel and move to the right, because they only want us to state, they never ask us to explain. Let's take a look at the answer. When NB becomes a magnetic north, since like poles repel, the north pole is repelled from NB. Okay, now the current in the coil is now switched off. Explain why the bar magnet is attracted to the soft iron core. Okay, that means this bar magnet will now be attracted to it. So it all comes down to this soft iron, easy to magnetize, easy to demagnetize. Now when my current is switched off, it stops becoming a magnet almost immediately. Okay, because iron is a soft magnetic material, when the current is switched off, the soft iron loses its magnetism and is no longer an electromagnet. Instead, it becomes an induced magnet due to it being near the bar magnet. NB becomes an induced south pole. Okay, since unlike poles attract, NB will now be attracted to the north pole of the bar magnet. Okay. By the way, someone asked me this today. This is north and this is south of a bar magnet. So magnetic field, if they were to ask you to draw the magnetic field lines, you have to draw it coming up from north and entering south. And take note, the field lines cannot touch each other. And if I have, so the strength is the strongest at the poles. As you can see, there are many field lines near it. But as you go further and further away, you see the distance between field lines get further apart. So this is weaker and this is stronger, right? Because the field lines, if they are close together, it means that the magnetic field strength is the strongest. So if I have a compass here, the compass will point in the direction of the magnetic field lines. Compass, it will point in the direction of magnetic field lines. Okay, so take note of that. Now come back to B. State why the core of an electromagnet is soft iron rather than steel. So this is soft versus hard magnetic material. Steel is hard magnetic material. That means it is hard to magnetize and demagnetize. Okay, so they just want us to state why. Okay, the soft iron loses its magnetism quickly once there's no more current passing through, while steel will retain its magnetism even after the current stops passing through the coil. So this is what we want, right? For electromagnet, once you turn on the current, it straight away become an electromagnet. If we turn off the current, it stops being electromagnet. That's the whole purpose. Okay, I will go through section B in another video because it may be too long.